An instrumentation amplifier is a form of a differential amplifier, where the inputs are buffered by two op-amps. It is designed specifically for sensor inputs with its variable high gain, high input impedance, low input offset drift, and high common mode rejection. It is commonly used to amplify small differential signals for thermocouples, strain gauges, and current sensors used in motor control. The pinouts are specifically set up for amplifying sensor signals. We'll go over the pinouts a little later. Let's take a look at the high-level design of an instrumentation amplifier. The inputs V1 and V2 are fed into two operational amplifiers. The resistance network of R1 and R2 will make them perform as two inverting amplifiers. The output of these buffering amplifiers is fed into a differential amplifier. Vout is the amplified signal for V1 and V2. R1 is a variable gain resistor, sometimes called RG in the spec sheets. You're given a formula in the spec sheets that tells you what resistor value to use for RG to give you a certain gain. The gain varies from 1 to 1,000 on commercial instrumentation amplifiers. Let's calculate the gain equation for an instrumentation amplifier. We use the principle again of superposition to calculate the gain, similarly to what we did for the summing and differential amplifiers. First, we will calculate the component of Vout directly from V1. We set V2 to 0 and we take amplifier A2 out of the system. Amplifier A3 acts as a differential amplifier with input voltages V3 and V4 and the resistor network of R3 and R4. Vout1 equals R4 over R3 times V4 minus V3. First, we solve for V3 in terms of V1. With amplifier A2 out of the system and V2 assumed to be a ground point, V2 plus is tied to ground. Because current does not flow into the input terminals, V2 minus must be at the same potential as V2 plus, and thus VB is a virtual earth. A1 acts as a non-inverting amplifier with current through R1 and R2. We use the formula for non-inverting amplifiers to calculate V3 in terms of V1. Then V3 equals V1 times 1 plus R2 over R1. We still have V4 as an unknown in terms of V1. However, we can find V4 in terms of V3 and do an algebraic substitution later. The current flows are shown with the letter I. There is nowhere else for current to flow. The inputs to an op-amp are of infinite impedance, so current cannot flow into the negative lead of amplifier A1. Amplifier A2 is out of the system, so current I cannot flow there. This forces voltage V4 to go below earth ground level, making it negative. Using Ohm's law to equate current I, we find that V3 over R1 plus R2 equals negative VR over R2. Then VR equals negative V3 times R2 over R2 plus R1. And now we have a way to substitute for V4 and V3 in the equation for Vout1 in step 1a. Time for some algebra. This slide shows all the algebra to find Vout1 in terms of resistor values and V1. Let's bring back our formula from 2 slides ago. Vout1 equals R4 over R3 times V4 minus V3. Then we substitute in the value for V3 calculated 2 slides ago and the value for V4 calculated in the last slide. We get a complex formula in terms of V1 and all 4 resistor values. Fortunately, the term R1 plus R2 appears in the numerator and denominator of part of this formula and cancels out. Combining terms, we are left with Vout1 equals negative V1 times R4 over R3 times R1 plus 2R2 over R1. Now, we need a formula for Vout2, the component of Vout coming from input voltage V2. This is a symmetric calculation, so we're mostly going to breeze through it. However, the next slides document the detailed calculation, which you can verify on your own. This time, we take amplifier A1 out of the system. We set V1 to 0 and calculate the component of Vout from V2. Amplifier A3 is again a differential amplifier, but this time with input voltages V5 and V6. Now, Vout2 depends on the difference between V5 and V6. First, we solve for V5 in terms of V2. VA this time becomes the virtual earth, A2 is the non-inverting amplifier, and V5 equals V2 over 1 plus R2 over R1. Continuing with finding Vout2 this time, we find V6 in terms of V5. The current flows are shown with the letter I. Again, using Ohm's law, V5 over R1 plus R2 equals negative V6 over R2, then V6 equals negative V5 times R2 over R2 plus R1. And now we can substitute for V6 and V5 in the equation for Vout2 in step 2a. More of the same type of algebra as before. We find Vout2 in terms of resistor values in V2. We bring back the formula for Vout2 and then we substitute in the values for V5 and V6. The term R1 plus R2 cancels out, simplifying the terms. We combine them and get an equation for Vout2. It's the same as Vout1 except that there's no negative sign. By using superposition, we find Vout as the sum of Vout1 and Vout2. The instrumentation amplifier is still a differential amplifier because it depends on the difference between V1 and V2. The resulting equation shows a gain term that depends on all 4 resistor values. The circuit designer adjusts R1 to get a desired gain, with the resulting gain determined from the formula R4 over R3 times R1 plus 2R2 divided by R1. Let's look at the AD8422 instrumentation amplifier. In this chip, R1 is called RG, which the designer adjusts in the circuit to get gains between 1 and 1,000. The chip has a high common mode rejection ratio, which allows it to keep noise signals common to V1 and V2 from showing up in Vout. The input offset voltage multiplies with the gain to produce an error in the amplified signal, so the lower this spec, the higher accuracy sensor reading you will have. Low noise distortion is important for low voltage sensor signals. Let's correlate the pinouts to our circuit diagram. Plus in is for the voltage that we had called V2. Minus in is for the voltage we had called V1. These pinouts would be for the plus and minus leads from your sensor. You place the resistor R1 across the 2 leads called RG. Plus Vs is the positive supply voltage to the amplifier, and minus Vs is the negative supply voltage. Vout is your amplified signal, which was also called Vout in our circuit diagrams. You can level shift up the output voltage by connecting Vref. The definition table for the pinouts shows you the formula for the gain. In this circuit, R4 has been set equal to R3, and R2 has been set to 9.9 kiloohms. Let's recap. Now you've learned how to use an instrumentation amplifier for low voltage sensors that need high amplification, such as thermocouples and strain gauges. In the next video, we will explain some important specs found on amplifier spec sheets and how these specs affect your sensor accuracy.